more. Actually, there were many questions on the CTLE day and day before. So let me just, for a recap, go to the CTLE part. So we have seen that the response of CTLE is ADC 1 plus S by omega Z 1 plus S by gamma omega Z and 1 plus S by omega P2. This was the response where your DC gain is equals to GMRL by 1 plus GMRS by 2. Omega Z was 1 by RSCS and omega P1 omega P1 which is equals to gamma omega Z, let me just write it as, is 1 plus GMRS by 2 times omega Z, and omega P2 was 1 by RLCS. So these were the parameters which we had, and we told that we need to decide on these parameters. And the method which I told that you start with a DC gain, pick up a DC gain, some value, whatever you need to begin with. And the second was you need to know what kind of equalization you need to do, which is you need to know the A peak by A DC, which will reflect the channel loss in the system. And the third thing I told that you know the peaking frequency, that omega peaking frequency is equal to your 1 by 2 times data rate. That's the Nyquist frequency. And the reason of choosing this frequency is that most of the signal energy is concentrated from 0 to Fs by 2, where Fs is your data rate. Okay, now the questions were that how do I find what is the placement of omega Z and omega P2 or gamma, and those things were that okay, you can choose it by hidden trial and you may end up in one particular place where you get the same loss. So now thing is, let's me just draw, this is a pretty good drawing. Okay, so I know what my DC gain should be, I know my peaking frequency, and it will be because of the second pole. This is just a Bode plot in logarithmic scale, mod of H of S. Now, the thing which I know is omega Z. If I pick up a certain omega Z, and what happened? Okay. In an ideal case, this frequency, let me call it omega 1 and omega 2. Omega 1 will be minimum of omega P1 and omega P2, right? Wherever it happens, ideally. And omega 2 is just the maximum of omega P1 and omega P2. And the parameter which we want is this, which is the A peak by ADC. This is a DC value. So the question is, okay, in what all other manner can it achieve this? I can also use this, right? So the requirement is that I should have this peaking value at your Fs by 2 frequency. This is the requirement. So I can also have some kind of transfer function. Let's say the same transfer function. It can be also like this. Means I can get the same peak value, A peak by A DC. Here I am now. A peak is this. A peak by A DC just that reflecting the channel loss. Is not reflecting the peak value of the CTLE transfer function. So how do I basically ensure that whatever channel loss I want, or whatever A peak by ADC I want, that is only the maximum value in the system. It's like a local maxima which exists there. Okay, so the thing is, even if you do this, even if you have the blue response in the system for a given channel loss, you will actually compensate the channel loss. There is no problem in that. Because you have, let's say, 20 dB channel loss, you make sure that at A peak by A DC at your Fs by 2 is the 20 dB compensation. Okay, but the thing is, if you are doing that, what are you trading off? The requirement is that I should have a maximum peaking value of only 20 dB, but you said, okay, I can have maximum different, but 20 dB at Fs by 2. Okay, so if you do that, then you will find that you will be trading off in terms of power. So putting an equation that d of d omega and mod of Hs at omega peak frequency, the frequency which I want should be equals to 0 ensures that that is only the local maxima in the system. So I do not want more peaking at a higher frequency. If you get it, it may turn out that it is better for your equalization, but it is also how much power do you spend in doing all that. If you are getting it for free, it is good, but normally you do not get anything for free. Okay. So, and the other thing is, the way I have plotted here is I have plotted as the Bode response, right? So you can say, okay, now if I do not want it means if I do not want a higher peaking local maxima, I can have the omega 1 and omega, like omega p1 and omega p2 at the same frequency. Means if they are at the same frequency, let's say at same as omega 1, you will have this kind of response, right? Okay, this is like, okay, let's assume this is minus 20 dB per decade. Both the frequencies are the same, so you cancel the 0 and you have the pole. But this is again a Bode plot. So what will actually happen is, actually if you put at the same frequency, you will have something kind of, sorry, this, right, in a real system. So once you get this, then okay, you will say I will shift it actually, and then I can find from that. So you can always try it that way, but that is more of a like iterative process to get it the right frequency. So doing it this way systematically, at least you can get a first assumption of what poles and zero locations should be, and then you can start using the other parameters. And the main goal of this, that this should be a minimum power design, because power is the cost here. If someone says I want like a 10 dB gain at 20 gigahertz, I can, if I have infinite power, I may be able to do it. But if the CTLE power consumption dominates the whole power consumption, then it's surely not a good design. Okay. So any questions on CTLE response? Because I found that there are many questions after the class. Anything? Okay. So let's continue our yesterday's discussion that was on decision feedback equalizer. Any questions on the yesterday's portions? Okay, so what we have seen yesterday is that if we know the previous estimated bit, if we know the previous estimated correctly, then we can cancel the post cursor ISI. That was the point which we took. So let me just draw it. So we have channel, and then let's say this is a summing block, and you have a comparator, and this is a clock comparator phi, and again W0. Let's say this is all subtraction, and then if you have more ISIs to cancel, you just delay the bit, and this is W1. So, and all these flip-flops are clocked at a data rate. This is the simplest implementation at a block level, which you can see. Okay. Now, the real implementation is little bit different, means you do the same operation but in a more feasible manner. You have a termination, and then you can say you have a GM block, which is now this is becomes a summing node. So I can just put a resistance RL, and then you have comparator, which is clocked at phi, gain W0. Okay, now this gain W0, now if this is the W0 gain actually becomes a GM cell, then it will directly add up to the summing node. This is V sum. This is Y of T. So now you have this flip-flop back again here, and W1, and you sum this up in all these cases. This is signs you can always take care of in differential by flipping the polarity. Okay. So this is the simplest implementation where the input V of T is converted to a current, pumping the current into the load resistance, and whatever bit you have decided, so this bit is de-estimated of n-1. Whatever bit you have decided, that bit is adding up a current into the load, and similarly the bits are delayed to cancel the post-cursor ISI. So let me just write the expression for that, where V sum is equals to GM times Y of n minus W0. Let me just write, if W0 is a current gain, W0 times D of n minus 1 minus W1 times D of n minus 2, okay, times RL. So now if Y of n consists of your cursor and ISI, so I can just write GM as V of cursor. V of cursor is like the main cursor, the current bit which I want to estimate, plus the contribution due to the ISI, minus, now all of this term, W0 into D of n minus 1 into W1 D of n minus 2, I can say this is equals to your I times DFE. This is all the contribution which is coming from the feedback tabs. Okay, times RL. Now what we want that GMV cursor RL plus GMV ISI minus IDFE. So what do we want that this parameter should turn out to be? Ideally 0, right? Any mismatch will cause you a residual at the input. So if that cancels to 0, what you have is GMV cursor times RL. This is the amplitude which you will measure at the input of the comparator. Okay. GM, so GM is the block which converts the input coming voltage to a current, and RL is for gain. Because, okay, we will come to that a comparator wants a minimum voltage input depending on its sensitivity, and it's the offset, whatever offset remains, you need to have a minimum voltage to resolve within a 1-bit period. So there will be a minimum limit on GMV cursor RL. So you can say that GMV cursor RL should be less than, sorry, not less than, but actually greater than and equal to V sensitivity of the comparator. Okay, and V sensitive of comparator is decided by your noise, offset, and what is the bit period. Because given infinite amount of time, a comparator can resolve a microvolt also, but within a bit period, how much can you resolve, that limits it. Yeah. How? Yeah. So those will be the difficulties which will come in, and you will compensate it somehow. So we will come to, so this is only, you see how I realize the GM, means I just put a GM block, How the actual implementation will come, I will just show next. Okay. So do you see that in this network is any other parasitic component missing at the vsum node? I am adding the GM block. I am adding all the taps at the vsum node. Is any other parameter missing? Component. Let me just ask you that. What else is present at vsum node? Capacitor. And that capacitor is a killer actually. CL. The more the taps which you connect to the vsum node, the more the capacitor you add at that node. So what actually happens? Your vsum node now has become GMV cursor RL into 1 by 1 plus SCL RL. Right? Pardon? Yeah, the more you are basically going to do that, it will add means it can surely lead to a better output swing, but the constraint is the delay. How much time delay are you having? So if you say if this is the total sum in current, right? So okay, let's just look at this, that all the current which is coming from the signal, let's call this as I signal, okay, and your IDFE. The one way is I sum this current and pass through RL, which I just did, and I told if I do this, I am having an additional capacitor CL, which is limiting the output value in a one given bit period. Because as soon as you have 1 plus SCL RL, you can say in order to settle to 95% of the final value, the RCL time constant for 95% settling, your RLCL should be less than T bit by 3. So this is actually called as time constant tau. Right? So if we do this RLCL, we have this difficulty. So what you suggest is that I can, in place of passing through the RLCL, I can pass it through an op amp. This is what you suggest, and I can do this. But think about it. If you are doing this, you are putting a block in between. Maybe the parasitic gain at this node has gone, this is very less CX or something. It's a very low impedance node. But this will require the amplifier to be much more wider bandwidth to settle. So final settling will be limited by whatever the capacitor you are having at the output node. Okay. And it is also going to add a delay. So here the importance is not only the gain or something. Here the importance is what is the delay from one delay in set. Like the settling period is the problem. Gain is not an issue. To an extent, gain, if you are getting the same gain with a lesser delay, that is the requirement. And the other thing is what you said, that I can put an amplifier. Actually, you do not put an amplifier. You will see in an improved version, you split the comparator. So any comparator has a pre-amplifier before the comparison happens. So have you actually seen any kind of comparator in CMOS? Huh? Back-to-back connected inverter, right? But that back-to-back connected inverter always is preceded by an amplifier to amplify the signal to a certain value, so that you can resolve the bit. So that will come later. But putting a specific amplifier in between the comparator and the summing node is actually going to add your delay. You need to be cautious. Means in some applications or some places it may turn out that this is the better thing to do, but it may not be in all the as the speed increases because of the delay. Okay. So the settling is surely a RLC is a problem in a high-speed decision feedback equalizer. Okay. Now, if we are talking of the settling, can you comment on the settling of this loop where you clock it, it has to resolve the thing, and within the next bit period, it has to finally sum up, right? So if I look at the delay, so for first step, T delay is actually equal to your clock to Q for comparator, right? Which is having a smaller input voltage at the input, plus your settling time constant, whatever is there due to the time constant RC that you should have, and then you have a setup time for the comparator that you should set up your final value what you want to compare, maybe 10 picoseconds or 20 picoseconds before the clock edge comes. T settle is the RC time constant settling. So if you look right, well, let me just show the block. You see when the clock comes, the comparator resolves that. But as soon as the clock comes, the output will not turn out instantly. There is a certain clock to Q delay for the comparator. So that is a clock to Q delay. And this clock to Q delay is dependent on the input swing, because this input swing is a small swing. Then the thing is, as soon as it gives the output, that current is being summed up in the VSUM node. And that summing up node is that settling is decided by RLCL, which you say that time constant should be like T bit period by 3 for a 95% settling or something. And then that value should be ready a setup time before, delta setup time before the clock edge comes. Okay, so you see that the T delay in the whole loop, this should be lesser than your T bit period. Otherwise, you can have an error. Whereas, if you look the second loop, right? Here, this is also a clock, but this is a flip-flop, which C is more or less a full-scale input. Okay, so this delay for second tap T delay is T flip-flop. Plus, then the same thing happens. You have T settle plus T setup less than T bit period. Huh? No, so you see here, right? Dn minus 1 is basically transfers to D of n minus 2 at the second. You are creating a finite delay element, finite delay between the first and the second bit, right? So you need to clock it. Means that if you do not clock it, then you have to manually, not manually, you have to have some kind of delay element which is tweaked to exactly 1 unit of delay, right? Now, tuning to exactly 1 unit of delay, the best way to do is you use a flip-flop which is clocked at the data rate which you want, so that at every clock edge, you actually change the output. So, but in all the practical circuits, as soon as you clock the flip-flop, your output will appear only after a certain delta time, right? So you are having, that is basically a T flip-flop delay. So if I just redraw the whole thing, there is a comparator where you are having some, let's say, limited input, and this is clock, and you have an output, let's say V, and I say the delay is T clock to Q for comparator, right? For the second tap, you are actually having a flip-flop, which is also clocked, but which sees more or less full-scale input, because Dn minus 1 is a digital signal. So you have like 1 and 0 signal. Okay. And you have this again output. So Phi and P. So this is T flip-flop. Now, which do you think will be larger? Huh? Comparator one, right? So T clock to Q is in most of the cases, I think, unless the flip-flop design is not too bad, you will have T clock to Q is larger than T flip-flop. And if this is the case, closing which loop is difficult? First start. So this actually makes the closing first loop most critical. And all the innovations in the DFE design are more or less they are aimed at this: how to close the first loop as fast as possible, or anything can be do with the first loop. Okay, so yeah, so you see that this T clock to Q is greater than T flip flop, and I want to reduce to T clock to Q, but the whole aim is to get a certain delta V swing at the output, right? Which is the minimum required for comparator. So let's see how does the actual implementation go, so that if we can do something with the circuit. So the actual implementation is you have an load resistance, and surely we do not use any active load normally because that adds more parasitics, capacitor and a current source. This is V in difference. Okay, and then you have, so now I am converting all the gains to current. Okay, so let's say this is D hat of n minus 1, and this one is, let's say, I naught, and this is I1. And if we are considering two taps, sorry, this one is, if we are considering two taps, so we have two taps connected here. This is I2, D of n minus 2, and all these signals are summed up and they go to a comparator, okay, which is clocked. Comparator output is actually D hat of n minus 1, and these comparator outputs goes, let me say, as a differentially to a flip-flop, which is clocked, and the output is D hat of n minus 2. Okay, and since you are having a resistor now also, you have a load, capacitance load in both the nodes. Okay, this is a very typical implementation of the DFE, which you just see here. Now let's see what is the difference between the different cells. So Vin is an analog signal. Okay, if Vin is an analog signal, we require, you have seen, right, that while cancelling the ISI, we require GM times V cursor multiplied in a linear manner. You can say V cursor is changing. It depends on bit pattern. So Vin is an analog signal which actually requires GM to be linear. Whereas, what do you think about D hat of n minus 1 and D hat of n minus 2? They are the estimated bit values which have 1 or 0. So I can say they are digital signals. Okay. Yeah. So if they are the digital signals, what will they do to the current I1? Can you comment? It will just steer the current in these nodes. If it is just steering the current, do we need a linear block there? No, right? Means if you are able to steer the current properly without doing anything crazy in the due to channel length modulation and other, that's fine. Okay, so all the tap cells or DFE taps, they can be non-linear. Okay, let me write not non-linear. They need not be linear. Okay, means if you make them linear, it will not hurt you, because you are always cancelling the same amount of current because the signal swings are the same. But making it linear is a more hard thing, so you can try it to be non-linear, and if you are able to steer the current, that is fine. Okay. So in this case, if linearity becomes an issue, what can we do for the first cell? Pardon? For the GM cell, if the linearity is becoming an issue, what is the easiest way to make it more linear? Huh? You cannot increase the input swing. If you want to increase the input swing, huh? Decrease the input swing, how much can you reduce from a 50 millivolts or a 10 millivolt swing? Increase the overdrive, you are limited by the supply voltage. You need a certain headroom also at the output. There is this basic linearization thing by resistive degeneration. Have you heard of that? So let me just tell you. So that resistive degeneration is having a resistance here, which is, let me just draw a few. I'm just plotting the small signal. If this is RS, right? What is the effective GM of this transistor? Let me write GM effective. This is equals to GM RS by 1 plus GM RS 1 by RS, right? Which is equals to, if GM RS is much greater than 1, it's 1 by RS. This is one of the conventional and mostly used way if you want to make a GM cell linear. Okay. The only thing is that this actually reduces your effective GM. So the comparison, the assumption which I have took here is that GMRS is much greater than 1. Then only I can get that value, 1 by RS, which makes it linear. But if GMRS is much greater than 1, that means GM is much greater than 1 by RS, and you can see the effective GM has been reduced. So you see the trade-off, but you get the linearity. Okay. Now you can implement this in two different ways. One way is that I use in this manner. The current source is like this, RS and RS, and the other case is, both will give you the linear GM. Okay, other case is this. So let's say this is I0 by 2 and I0 by 2, and this is I0. Same resistance. You get same GM in both the cases. Small signal. What do you think is the trade-off between type 1 and type 2? Power dissipation. No, I'm burning the same current in the two. No, but if you are looking for the power dissipation, the I naught current is flowing from the same supply, VDD. Means right now just consider, let's say, heating there, but the power dissipation is the same, right? Any other thing? It reduces the headroom for your output swing. Okay. So type 2 actually has a lesser headroom or lesser volt swing margin at the output. But what is the benefit? Huh? GDS, you can say you can dominate the GDS by RS. So GDS will appear in both the cases, right? Which GDS? Oh, okay, the current source GDS. Type 2 GDS will not matter, so you have the GDS appearing of this transistor here in a small signal. You have GDS appearing of this transistor here for the input pair. Bias, yeah. So for the bias, GDS will be there, but this is another point, but normally the current source is GDS. You design the current source such that they are not affected by the channel length modulation. That means your GDS is actually pretty low so that your impedance, output impedance is high. But surely that point is there. What else? What can you comment on the noise of the current sources in the two? So I have the noise IN1. Let me just write it as IN1 and IN2. And let's say for this, I call it IN3. So what about the noise due to the current source in type 1 and type 2? Which will contribute more noise at the output? Why? And what will happen in type 2? Common mode noise. If you're looking at a differential signal, you do not have any noise in type 2. So type 2 is less noisy. Okay. So you see the trade-off. You are basically getting a lesser noise in type 2, but you are trading off the headroom. Now, whichever becomes dominating and what parameters you need, you will design as per that. Okay. So this is regarding the linearity of the GM. Now let's look at the settling. We just say that this is dependent on RLCL. So, and there is a minimum requirement at the output of the minimum requirement at the input of the comparator, which is also the summing node. So let me just write it that equation again, that your V sum is equals to GM times V cursor. Let's say all the current is getting cancelled. RL into, so in this is in actually the Laplace domain, SCL RL. Okay. So in time domain, you have V sum of t. Now I'm considering only 1 bit period in this case, because from bit to bit period, your IDFE changes depending on the bit pattern, right? So this is equals to 1 minus e power minus t by RLCL. Now this value should be equal to, as we have seen, let's say delta V for comparator. Comparator at the end of 1 bit period, t bit. You just keep using the same, right? So if I assume that it settles to 95%, and I say this is equals to, let's say, GMV cursor, RL is equals to delta V, which is required. Okay. Delta V is a requirement which is forced by the comparator. Now, GM is equals to delta V minimum Okay, let me just say the same as delta V minimum. I'm using different notations by V cursor RL. So if delta V min increases, what do I need to do for the same circuit? If delta V cursor, the whatever is coming from the channel loss is the same. If delta V min increases, what pitch parameter do I need to increase? Is either you increase GM or you reduce RL. Is not reduce RL. You have to increase either GM or RL or both, whichever way it works, right? But increasing RL is actually going to, if you increase RL, you have a settling issue. Okay. Now, if you increase GM, so there are two ways you can basically overcome the, not overcome, you can have actual delta V min, increase delta V min. If you increase GM, what does that lead to? More power consumption in GM cell, but this is not the end actually. If you see that this equation, right, the one which I have, this one, you see that GMV cursor and GMV ISI minus I DFE. So if I increase GM to get the more swing, I am also increasing the contribution from intersymbol interference. So I have to increase IDFE. And if I increase IDFE, what will that do? That will add. So in this case, if you so it's like this. If you increase GM cell for more current, you have to increase the tap weights. And if you increase tap weights, you are going to add more capacitance at the output. Just the parasitics. Huh? No. So the thing is, if you increase I1 also to steer that current, so think about it. So this design is like when you design, let's say for 100 microampere of current, right? Your switch sizes will be minimum or whatever minimum switch size to steer that current, maintaining the voltage headroom. Okay. Now, if you want the same switch size to carry 2x of the current, right? Their overdrive will change. So think that each smaller value is optimized. You cannot decrease the size of that less than that. It's not that I keep on. So the thing is that tunable, you can have a tunability on one particular range, but you cannot have the tunability if you increase the current by let's say 10x. You can have 2x, but any tunability is coming at the cost for the maximum current which you want to carry. Okay, so if you have a design which can carry a minimum current, an optimized design, and you want to scale the current, it's like you scale the whole cell together. And if you scale the whole cell, then you will have a more added capacitance at the output. And this capacitance is not only the parasitic capacitance, this capacitance will also come from CGD, CDS, means the transistor's own parasitics, rather than anything else. So there is a limit that you can get a minimum delta V min at the output of the summing node because of the yeah. Mm-hmm. So we use D of hat as 1 volt only. So this the input pair. So this that's why I wrote here is right that D hat of n and D hat of n minus 2 are digital signals, and those digital signals will mostly they will be working at the supply voltages. They are not. Huh? It will increase or decrease the headroom. So if you say that it is going to decrease the headroom, I can say I will use a optimum voltage such that the headroom remains fine. So I will decide my switch size such that my headroom is there and I do not cause any problem due to the channel length modulation also, and the size is minimum because the parasitic capacitance is important here. So if you are just operating it as a switch, if you are, let's say in this particular example, your headroom is 0.6 volt from the supply of 1 volt. So 0.6 volt is a common mode voltage. Now for 0.6 volt common mode voltage, I will design the input pair for the taps such that when they are steered to one side, you steer the current without causing any change in the headroom. Now if on top of that, if I want to scale the current to 2x, the one way is I just scale the current. But if I just scale the current, then either I have to increase the gate voltage of the input pair. But increasing the gate voltage of the input pair is not an option because in the first place only I designed it to be an optimum one. So the only way is you take the multiple cells and like you can say it's a parallelization. You just take the multiple cells and connect node to node. That is not going to change any of your circuit parameters. Okay, so that is where you can say if I'm doing that way, I'm adding more capacitor. But for a given design, if you want to vary the current by delta plus minus 20-25%, you can just scale the current. But you always have to keep in mind that whatever is the maximum current you will steer on one side or the other, at that particular point, the transistor which you want to remain in saturation, they should be in saturation. Otherwise, you will lose the linearity. So it's like if I go and increase the current, tap current at 5 times, so my common mode voltage for the input pair will drop and my input pair is going to be in a triode region. So that I cannot have, like that is not good for the system. Okay. So what you have seen is that the current which is actually going into the summing node is equals to Gm times V cursor plus GMV ISI minus IDFE. And IDFE is and you have this as a ZL right now I'm writing, which is a combination of your RL and CL. So ZL is actually going to put a limit on the system. So just previously we have seen that we have this I sum current and we want to create a voltage delta V for the comparator. Right? This is the need of the design. And one way we have seen is I replace this, I basically pump it in a resistance and RL and CL actually comes into picture. Huh? Delta C or delta V? ZL is the load, which is RL, CL I have put in here. Oh, sorry, that's the load. That's not the current. This is only the current. And it's just stored as a voltage. So this is the current which is going into the summing node. And the way I created it previously, the voltage was I pass it through a load resistance and I got the voltage. But CL comes on its own and I land up in a settling issue. So what is the other way you can think of generating the same voltage, generating a voltage delta V using a current? Take what? So this difference is being done here, right? So if you if you are saying, so let me just say this. So this block, right? If you just remove this block from the system, you are actually having the sum of all the currents. So your current is from this node. It's just because you pass it through the load resistance and the capacitor, you got into settling issue. So I have the sum of the currents. I want to generate a voltage. The way I have tried is I have just passed it through a resistance to generate the voltage. And for passing it through a resistance is the simplest option which you can exercise. So my question is this. I have the current, I want to generate a voltage, which is the other simplest component I can generate a voltage in a given bit period. Capacitor, right? So I have this I sum current, sorry. Okay. I have the I sum current, I pass it through a capacitor and I wait for 1 bit period and I compare. So this is delta V. So if I just want to write, let's say V, let right now I just write it as V out. Oh, V out is the comparator, not the V out. Let's say V integrated node. V integrated is equals to 1 by C integral of I sum dt from 0 to t, right? And this is equals to I sum times t. This is right, no? And this needs to be equals to delta V, what we want. Pardon? First two taps need to be. So all the taps, this is the current of all the taps. No, in first step we are always, so in the previous one also we give a 1 bit period. Yeah, now the thing is, what is this integration capacitor? So let me just ask you this question. In the previous case, this capacitor was CL. Let me start with the same CL. Just to begin with, let me start with the same CL and see whether the output swing is larger or smaller for the same ISM for the same bit period, but not using any resistor, but it's like just integrating it. Okay. If it turns out to be it is not the good, if it is like 2x or 3x or even lesser than the RLCL, then this is no good. But if it turns out to be better, then it will be good. And if you can think in just a simpler manner, in the previous case, you have RL and CL. Okay. And you have, so let me just say, you have a ISUM node, you have a resistor, and just consider this, you have actually a switch here. Okay. RL and CL. And in the other case, you have the same CL and a switch with a current source. Which node do you think will attain the same voltage faster? Huh? No, same current in the two. Same current, same capacitor, just an added RL. So look this one, right? You have, if you look the exponential version of means when you are settling, you have something kind of this. Means in case of IL, this is will just keep on, or I it will settle to I times RL, the final settling value, right? And what is the slope at the input? This is a linear. I by C. So you have, let me just write V out is equals to your IRL into 1 minus e power minus t by R LCL, right? So dV by dt is equals to IRL into, okay, you do the differentiation 1 by RLCL and you will have another value which is, so you want to this to be, this is plus, let's say you just calculated t equals to 0. Okay, if you calculate t equals to 0, this is the value and you have IL by CL, I by CL, sorry, right? So you see that this slope is always greater than when you are settling with an RLCL. So at least with this simple example, the first thought should be if I do not do anything, if I have only CL, I may be able to attain the same thing faster. But what are the drawbacks of this? We can see it later. Okay. So let's stop here and I will continue tomorrow.